Okay, so first and foremost, I don't know the level of various students here in terms of your just your Python coding skills. Can you folks just like type in like, hey, how good how long have you guys used Python? It could have been anywhere from 0, 1, like a few months, just recently, some Code Academy, you work with it. Just type some stuff in. So this way I get kind of like a little bit of a snapshot here in terms of the population pool joining us. Okay. All right. Okay. No. Okay. So it sounds like folks are roughly at about the same level, which is great because it makes it easier for me to kind of align what we're going to do in today's discussion then. So just first and foremost, I want to address that today's session, I chose to make it a little bit more on the foundational elements of what you need to do to work with text data. This way you can find it immediately useful to basically already take away and immediately start implementing it for when you are working with text data. So we're not going to look at things like neural networks or anything like that. We're actually just going to look at, okay, if you have text data, what are you going to do with it? And what steps should you look to take? Okay. In terms of the code, I'll explain as much of it as possible in a way that makes it fairly straightforward about what's going on. And first and foremost, the main library that we're going to end up using is NLTK. Now, NLTK is actually has a database where it hosts actually a large amount of files. Rather than have you download them all one by one, you could just do this one-stop shop. So this hashtag here, when you see this hashtag, it basically comments and says, okay, don't just treat this as like notes for people to read, and they could kind of look at it later on and know what your code is doing. So if you uncomment this out and you run this line together, you run these two lines together, and if you do this in Jupyter, NLTK is already in Jupyter Notebook. You shouldn't have to pip install, if I recall correctly, but just in case you are getting an error with with import NLTK, you'll also want to run this line as well, which is explanation pip space install space NLTK, and it's really, really fast. You could do this right in this specific notebook. Okay, so in fact, I will even put it in this cell as well. So I'm also going to comment this one out. So when you run this line, you're going to get a pop-up, and actually, so you might not notice it because it's going to just not show up here. And what you could just do is go to that pop-up and click just download everything. Just select all and download everything. You just run it on the background while I'm yammering here. Okay. So since I already have it everything installed on this machine, I'm just going to import NLTK, and it'll take a little while because I have a lot of stuff downloaded, obviously, because I already downloaded everything from NLTK, so it takes just a little bit. Okay, so that's the main library we're going to end up using for today. Now, when you first get text data, well, of course, one of the big challenges to work with text data is you need some way for your machine to communicate it with it in some manner. We can't take the word one, for example, and have it automatically understand that, okay, well, the string 1 equals 1. So we need some sort of interpretation for it. So as a result, very often the type of data you deal with when you're talking about text data tends to come in like some sort of what we call document format. And that document format can come in the format of, say, a sentence, a paragraph, an entire book, or what may have you. So one of the main things you need to do with this document is you need to split it to essentially individual characters, or you could split it into actually, for example, 2 characters or 3 characters. We're going to talk a little bit about that later on as well. But we're going to just look at the most basic way, which is we're just going to take a text and split it into individual characters one by one. So this is nothing more than actually just you could take any specific sentence. Well, actually, you could take any specific string, and you could basically tell it to, okay, split this string up according to whatever I put in here, whatever rule I put in here. So for example, if my string is full of, say, let's say commas, I couldn't actually just put in that I want to split it by commas. But in this instance, the default is it's just going to assume that you're feeding it sentences. So what I'm going to do is just leave it blank. And if you leave it blank, it will basically split it apart by these spaces, these empty spaces that we see here. So if we just run this code, you can see as above already. Okay, pretty straightforward. You see the output right here. So what ended up happening is we took the sentence and we made it now instead into a list of individual characters. We can actually do this automatically using a library. Instead of writing a Python command, we can just use a library and just kind of do it automatically from the library tools. So the tool that you can use from NLTK is nltk.tokenize, and you're going to import in this word tokenize. And that's because the very first step you do with any text data is always going to be tokenization. So which is this very process we're looking at here. You're splitting up a document into what we refer to as individual tokens here. Okay, so we do this from word to nltk.tokenize, import in this word tokenize, and then once we have this word tokenize, is a function. So what does that mean? You can just run this function, and function it literally just looks like the math function that you're used to from either your recent mathematics courses or way back in when you first learned about it in, like, say junior high or high school or whatnot. And literally it's just like this is a function f of x, right? Where we have this an input in. So same exact idea here. We have a function called word tokenize, and we have this input here, sample text. So once you got this this list of tokens, you're going to notice, well, when we want to do something with in terms of analyzing this text, there's a lot of useless stuff here. For example, what might be some of the text here that you don't really care about, or the tokens here that you don't really care about? Let's see if some of you guys can kind of find where I'm going with this. So what are some of these some of the tokens here that you probably want to discard? Yeah, for example, this punctuation likely isn't that useful, so we likely want to discard that. Anything else? Okay, so there are other words. For example, this is an A. They're sort of ubiquitous across all your text, so they're not really that. They don't provide us too much information. Say I'm examining. Let's say I examine. I'm trying to analyze data that I scraped from the internet. So I pulled all this information. Maybe I web scraped it, various news articles from the internet. I'm curious about, well, what those news articles are talking about. So one potential easy thing I can do is just create a word cloud. But you don't want your word cloud to be dominated by words like this and is. They're quite useless as far as analysis is concerned. You'd rather know more about the word cloud be dominated by topics within your text. So as a result, what we want to actually do is once we tokenize, we want to strip away all those unnecessary words, those extraneous words that we don't really care about. And we actually refer to them as stop words. So stop words are nothing more than just a gigantic list. And you're going to actually see this list right here. It's just a gigantic list of essentially words that are just ubiquitous across the board in the English language. And you can actually import in stop words from other languages as well. I just happen to be importing it from English here. So what you can then do is once you know, okay, well, I don't want any of these stop words, what we're going to do is essentially this filtering step. We're essentially you can think of it as we pass now all our tokens and we pass it through the sieve, and anything that makes it through is going to be the ones that are likely top words I actually care about in terms of analysis purposes. Anything that doesn't is because they're in this little list. And actually, this is pretty straightforward about how we're going to do this. So for example, here, I made my own list of stop words, and I made my sample sentence here. So what did I do? First thing I'm going to do is I'm going to tokenize, just like before. I split this text into its individual tokens. And then I'm going to join these tokens back, but after I actually pass this through this filter here. So see, as you can see here, if the word, the lowercase version of that word, so I'm lowercasing everything, so this way this and this are treated as the same exact word. If they're not in this list, then give it back to me as in my stored in results. So that's all I'm doing here. So as you can see, when I pass through this toy example into into this command, I'm left with these words into this sentence. So now I just have toy example, illustrate example below. And of course, I could have also added the punctuation in as well in this regard. Okay. So you could do this naturally with the package NLTK itself, just importing the stop words from here, and then essentially just make sure that I run these commands. And then here, as we can see, we could take a look at what the stop words look like, and they look like the stop words here. And then you could just use them the exact same way. Okay. So that's essentially the first two steps of what you're going to do when you're dealing with text data. You're essentially going to be taking your documents, you're tokenizing them, and you're getting rid of extraneous words that are more or less ubiquitous against articles. And you can actually choose to add on to this list of stop words with your own stop words. For example, if you are reading a lot of art, you're parsing a lot of articles that's about data science, chances are you're going to use data science as a stop word because you don't need to know that your articles are mostly about data science. You might be more concerned about, hey, is most of my articles that I'm parsing here dealing with maybe machine learning? Is it dealing with maybe something like time series? Is it dealing with maybe big data or what may have you? Okay, so once you actually get all these, make it through the tokenization process, one other thing you'll note is that, well, suppose I have, say, once again, a normal document has all sorts of text here and so forth. And you'll note that, well, we can end up having, like, say, writing as its individual token. We can have write as its individual token. We can have writer as its individual token. So what ends up happening? You have this gigantic amount of text data then. But most of it end up then being repetitive in that they're actually different versions of each other. So you get into lots of different issues here from the machine learning side if you decide to implement machine learning. But it's also going to be very annoying when you're just working with text of that of data of that amount of size. So what do you want to do instead then at that point? Well, it makes sense that I actually want to convert, say, all the words down to its root words. So for example, I can turn, I want something like writing and writer and what may have you all into just the root word write. So that very process is what we refer to as stemming. Now stemming, depending on the type of stemmer you use, is actually going to be, is sometimes going to trim a word down to just its root, but actually give you something that doesn't make any sense. So what I mean by that, it could end up say, for example, let's say I want to end up doing stemming on the word reading. Actually, reading is a terrible example. Maybe flying is also not. Let me think of a word that ends with verb that ends with e. I don't know why I'm having such a hard time besides the word write there, but I don't want to use the word write. Okay, for the sake of I need a word that, yeah, drive. That's a good one. So suppose I have something like, say, driving. Sometimes what I'll end up doing, now driving will actually convert to drive properly in most stemmers, but some stemmers will be what we call really aggressive, which is they'll try to stem words that it doesn't even recognize. So what it will automatically do is it will recognize some sort of pattern where it may be a word that can be stemmed. It will automatically turn it into, say, driv instead. So as a result, what you can end up happening is that you'll be running these words through a stemmer, and then you're getting back words where it actually doesn't look like words at all. So we'll talk about that in a little bit. But ultimately, actually, it doesn't have as much of an effect as you think. Because, for example, if you're choosing to analyze text, you could usually do some sort of additional coding to clean up the text after you do this what we call this pre-processing stage of the text itself. Or if you are tossing it into a machine learning algorithm, it actually doesn't matter if the machine learning algorithm sees drive versus, say, driv. Okay, it doesn't actually matter. So, but that's something that you want to be aware of when we're running stemmers. So just out of curiosity, when I talk about this part a little bit more in detail, how many of you guys here know what a regex is, or regular expression? Regular expression. Anyone? Okay, somewhat. Okay, so one of the things you can actually do to kind of clean up your text is use a regular expression. A regular expression is essentially just, it will be a pattern that you want to match up. So for example, your pattern could be some words that end with ing. That could be a pattern. Your pattern could be something like, I want something, for example, if I want to find a telephone number, the pattern will be something that looks like 0 to 9, x3, and then with followed by a dash, and then etc. etc. Okay, just kind of like just a layman's example of regular expression. So you could use regular expression to actually clean up your text here. But if you were to use a regular expression, for example, to follow the rules of stemming, it actually is quite annoying to write. So usually it's just better just to import in a stemming package. So what I mean by that is, if you notice here, I am writing a Python string. Now, if you did the regular expression to convert where it matches ing and turns it into an e, you'll get I am write a Python, and then this part, instead of string, you'll just say STRE, which is, of course, not what we want, because we want it to know that, okay, string is its own word, but I want to convert anything that looks like a variant of writing to the word write. So that's basically what's happening in terms of stemming here. And what I did here is basically I imported in a stemmer. I'm going to call it I'm going to import in the Porter stemmer. There are two stemmers that you could grab from NLTK. There's actually a few, if I recall off the top of my head. There might be more than two. But these are two of the more popular ones. So you're importing this in, and now I turn it into what's referred to as this stemmer object. And this stemmer object has a function called stem. And what am I doing here? I'm doing, essentially, I'm writing out my command. What I'm doing here is I'm saying, okay, stem this variable. So this variable is what I'm just going to call word, but it could be any placeholder you want. And as long as this placeholder is the same thing as this placeholder, it's fine. So I'm saying, so for every, run this function on word for every word in this tokenized list. So you can see that this is kind of like where we're doing a little bit of we're putting everything together now. So prior here, we tokenized our text. We turned it into a list. So what we did now is we're basically saying, okay, we can't stem this sentence as a whole. That's actually impossible because they'll treat it as a single word. And this word doesn't make sense because it's not a word. It's actually a sentence. So as a result, what we actually need to do, and this is why you need to tokenize, is we need to split it up into its individual words. And then you're going to stem each word at a time. So this function here basically says this part here that I'm highlighting, just this part, is saying go through each item of this word. Once it's broken up into a list of tokens, go through each of those words, and then find the stem of each of those words. And then at the end here, what I'm doing is I'm doing this join so that I can combine it back into this sentence. And of course, this sentence is entirely grammatically incorrect. But we're going to ignore that. Okay? All right. So another thing you can actually do that's more powerful than stemming, due to the issue of what I mentioned about stemming prior, where sometimes they'll trim the word to something that doesn't look very interpretable. So suppose you want to make a presentation of your text. So maybe you want to make a word cloud, or you choose to make maybe a bar chart of words that are most words and their frequency. So you want to identify your most frequent words to, say, a client. Well, then in those instances, you don't want to give them necessarily a bunch of just stemmed words because it will look really ugly. So what you want to do instead is do what's called lemmatization. So you only need to do one of the two. You either stem or you lemmatize. Okay? So because lemmatize actually already does the stemming for you. But what lemmatize does is it actually goes one step further. It stems it, but then it basically does a lookup. It searches in its dictionary and looks to see if there's any matches of that stemmed word to an actual word. So for example, what can I do? Observe. So we're going to import in this WordNet lemmatizer. We're going to do the same thing. We're going to create this lemmatizer object. So the reason why you need to create these objects is that's how Python works. Python being object-oriented programming means you need these objects. These objects can now do things. So it's almost like you're you can think of it as you're hiring a worker, or you're having a buddy. You're getting your buddy, and your buddy can either have attributes or can do or he could do things for you. He or she can do things for you. So in this instance, I got this lematizer object, and it can do different things. One of the things it can do is do this lematize function. So I'm going to use this lematizer object to run this lematize function on the word feet. And what does it do? It's able to say, okay, let me search for a bit, and I'm able to find back that feet, lematize, is actually foot. So this is the base word that you see here. Okay? So that's basically what lematize is going to do. If you put in and you try to lematize a word it doesn't find at all, basically such as over here, it'll just give you back its root word. It doesn't know what to do with it, or rather not its root word, just give you back what you already put in as input. It just doesn't know what to do with it. Okay, so this is all that you need to do in terms. These are all the steps you need to do in terms of working with text in some function. Now, you might hate me because of what I'm going to tell you next, which is there's a lot of packages that actually do all of these steps all at once. So as a result, you might end up thinking like, why do we go over all of that? It's because when you are actually looking to, say, take your hacking skills and your coding skills, your data science skills to the next level, it's much more important for you to actually understand what things are being done underneath the hood. So this way you can actually control what's going on. And on top of that, you also are aware of what's occurring, what's being passed as inputs into whatever function or model or task you're looking to do. So for example, suppose I want to run a machine learning model. What you could do is you could simply just copy and paste the code that I have here on your text data, and then toss it into all of that text data into a machine learning model, and you're good to go. However, if you were asked then, well, what actually happened there, you're going to be a lot more hard pressed to explain to someone what's going on there. And that's not usually something that is going to be passable in terms of the actual workforce. Folks are a lot more invested into the logic behind and the explanation behind what you're attempting to do versus just the final result. Because otherwise, they can't trust your final result. Your result's just going to be some number. And for all purposes and intent, you could literally just write a fancy script that prints that number out at the end, regardless of any modeling that's going on. So that's just kind of like a very hyperbolic example, of course, there. So what do we do with all of these text data then? What we're going to end up doing is, well, chances are you're curious. Well, can we use these words to predict something? And the answer is yes, you can. You can actually use words to predict. For example, if you get various documents, you can actually predict what subject those documents are, provided you have some sort of training data for it. Okay, so for example here, what we're going to do is I'm going to import in this well-known data set from sklearn, and basically these are news group data sets. I'm not certain how many of you guys actually know what news groups are. Might be dating myself a little bit, but news groups were essentially one of the main communiques back in the day about to share various topics and resources between academia and also just internet forum exchange as a whole. So we're going to grab all of these news group data that they have in this data set. And you don't need to worry too much about this part right here. This part is not it's more of an sklearn thing than anything else. So that's for a totally different topic. So basically what I'm going to do in the next few steps is I'm going to convert all of this data into a matrix, okay, into a matrix format, or more specifically, it's actually a data frame where it happens to have the variable stored in the matrix format, okay? So I'm going to basically just be doing all of that. But just as a quick snapshot of what each row of your data is going to look like beforehand, each row initially is just going to look like this. It's going to be this, effectively speaking, this document. And you can see this document is just a paragraph. And it's not even actually a paragraph. It's like all sorts of stuff. It got the email address here. It's got like a subject line. It got escape characters, and so on and so forth. Okay, it has all of this stuff, as you can see here. And what we're going to do is we're actually going to take lots and lots of these paragraphs or these documents, and we're going to essentially these documents are already bucketed under certain categories, and I can actually prove to you. For example, if we want to take a look at what those categories are, we can just simply say data, target names, and voila. These are all the different categories of these specific data. Okay, that just means Unicode. It means that the string is Unicode. That's just the format. Okay, so we now, since these are all our different categories, we want to try to see, well, if we train a model on data that looks like this and is attached to each individual category, can we predict new text? If we put new text into our model, can it try to bucket that text into one of these categories, assuming that the text fits in one of these categories in the first place? Okay, so that's what we're trying to do here. So what are we going to do? We're going to actually import in two ways of essentially transforming these documents into a matrix notation, some sort of mathematical notation that you can then use a mathematical model on. So that step is essentially called word embedding. Okay, that step is called word embedding. It's all the way up here. I skipped all of this because I want to try to keep this a little bit high level. You can just read this later on down the road. Okay, so there are two different word embedding methods that we're going to look at today, and they're actually quite similar. One is count vectorizer, and one is called TF-IDF. Okay, so I'm just going to run these commands for now to basically do the transformation of my text, but I'm also going to show you a little bit of what's actually going on. Okay, so word embedding is nothing more than actually, for example, the word embedding that we're doing here is actually nothing more than just taking counts of an individual token and recording that as a input in our data frame. So that's what count vectorizer is. So suppose you have sentence 1 is just computer, computer, computer. So let's pretend that we have 3 different documents, okay? And sentence 1 is computer is a list of computer, computer, computer. Okay. Sentence 2 is a list of, or rather, it was a sentence that have computer 5 times. So we're just going to put it 5 times. So this, I can't think of a sentence that has the word computer 5 times off the top of my head, unfortunately. And the word Python once. Okay. So, and of course, other words. Pretend it has other words in here as well, because these are meant to be sentences, not just random words, obviously. So it goes through and reads these sentences, and it says, oh, computer, 3 times. I see the word computer 3 times in the sentence. I'll mark it here. I don't see any instance mentions of Python, so I'll mark it as 0. And then here, sentence 2 says, okay, I see the word computer 5 times, so I mark it here. Python once, so I mark it here. And remember, how do we get these list of words? Because we did a step really early on in our pre-processing. What step do we do to get these kind of like lists of words? Let's see if you guys remember this. Does anyone remember? Folks remember it? What do you do to, what do we actually presumably do to actually transform our documents into these specific sets? Okay, well, we did tokenization. We're going to assume we did tokenization to actually get it to this specific format. Okay, so as a result, we got now this. We're going to get this data frame of, say, each individual token and then the counts of each of those tokens. And that's actually what count vectorizer is. That's what this process is. So as you can see here, nothing fancy. Okay, TF-IDF is basically taking this step, taking this one step further. Basically, it says, okay, if your word computer is the same amount in all of these, in each of your documents, we're going to penalize it. So that's basically what TF-IDF does. It basically takes your sum of words, but then it penalizes it by the count of the words across the board. Okay, and there's different types of penalization TF does. I'm just giving a very naive one. There's actually different. There are various different TF-IDF methods. I'm just giving you one of the more basic explanations here. So once we actually do this and we transform our text data, we're going to be able to actually then do some sort of modeling with it. We're going to be able to say, okay, well, now can the newsgroup data, can that data be used to as a training sample to then predict whether or not there are, if I feed in new articles, whether or not they are one of these categories. Okay, can we build a model for that? The answer is unsurprisingly, yes, we can, because we're going to basically use the same approach that you likely use even as a person to say, tell if something is going to be something, which is if you spot, say, for example, let's say you are opening up your emails or you are, and nowadays they're even hitting your phones. So you're reading your text, and all of a sudden you see this text message, and you see the text message just starts off with something like free, blah, sign up now, free, blah, 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 okay? And that's how your text looks like. And so automatically, if you see this email or you see this text, what are you going to assume is this text? The moment you see, like, say, free, like in so many mentions of it, you're going to assume that this text or email is exactly, you're going to assume it's spam or a scam of some sort, etc. So this is a very basic idea. This is the most classic example of that people use when they're discussing naive Bayes. Okay, which is if we know the probability of something already as a prior, we can then predict something else based upon that. So we're going to use a version of naive Bayes here that's very common for working with text. It's called the multinomial naive Bayes model. And multinomial is basically it's the prior distribution that it assumes that it's getting, which is, of course, when you're working with text data, multinomial distribution. It's basically saying, like, you could think of multinomial distribution as you're recording the distribution of, say, values when you roll a die over and over and over again. So that's an example. Okay, so we're going to be using this model, and we're going to be taking a quick look at whether or not our model can, given the data that we feed in, can it predict one of these? So we prior here, we already took all of these various text data. Okay, we took this text data, and we fed it into essentially we split it up. We split it up into this training set and this test set. And what that means is we have this training set here. Okay. Oh, there's no you don't see this test set yet. So we have this training set, which means we're going to use only a portion of our data, because we're going to look at the portion that we don't look at is going to be the one we're going to see, like, we're going to pretend that that's new data. That's how new data is going to look. So as a result, we're only going to use a portion of our text of our documents as training data for our model. And then we're going to fit it, and we're going to match each of these articles. They're going to be matched against its response. So in other words, each of them is going to be correct. It's going to have the data and its labels. Okay. The ratio I think I used is I don't actually remember up here. Oh, it doesn't say. I think the default is 60-40, if I recall, the default one. In this from sklearn, when you use the sklearn standard splitting of training into test. So you could certainly adjust it yourself, but right now we're using 60% of the data, if I recall correctly, from the defaults in terms of sklearn. Okay, so we're fitting it, and now what we're going to do is we're going to have, so we have this model now. We have two models. We have this model that's where the word embedding is simply just to count, and we have another model where we actually do the TF-IDF transformation as well. Okay, so one of these, we have two different models. They're both actually using the same machine learning model, but the input data is slightly different. The input data looks slightly different. One looks nothing more than just the raw counts, and the other is going to be the percentage distribution. Okay, so that's what this one is called, and this one essentially called. It's because you can use multi-class logistic regression. You certainly can. However, multi-class logistic regression has various assumptions that if you try to apply with text data of this nature, it will unfortunately fall apart. So it won't work as well. But you certainly can use other models as well. For example, you can actually use KNN. You can use support vector machines. You can use various neural networks. You can use a lot of different things to actually predict. We're just picking you could consider naive Bayes your benchmark. So in other words, if you try other models and you cannot beat the naive Bayes, then you know those other models are likely there's some either your pre-processing step needs additional work, or those models are not ideal based on the assumptions those models require. Okay, so what we're going to do now is we have these two models. So what we're going to do is now I copy and paste the two Wikipedia entries. Okay, I copy and paste the two Wikipedia entries here and here. So we have two different paragraphs about Wikipedia entries. And if you were just to take a guess off the top of your head, what should these two paragraphs, what category should they go under? What genre or subject? Okay, correct. Nonfiction. They're definitely nonfiction. But individually, which of these categories do you think they will fall under? Oh, let me text is on the smaller end. Here you go. Sorry guys, I didn't realize the text was so small. I could have actually expanded. So code must have looked, the coding part looked terrible. Then I apologize. Yeah, religion and probably electronics of some sort or something technical. Hopefully you guys will say computer graphics, because you see that it says GPU here. Okay, and you will hopefully you kind of see that as well. So if we were to now actually pass this, whoop, my new docs is not defined because I didn't. If we were to pass these two paragraphs in to our model as inputs, well, first we can't, because if you pass these paragraphs in directly, your model is going to be like, I don't know what these are. These are paragraphs, and I'm used to mathematic matrices. So what I'm going to do is I'm going to actually use the count vectorizer approach and transform these to now both count vectorizing and TF-IDF. So we're going to transform them into these the matrix formats that our model can take. That's what we're doing here. And then we're going to try to now use those new data in and predict with them. And so we're going to store these predictions. And if you can actually take a quick look, you'll notice that, oh, look, both of these were able to label the first one correct, and the second one, something went way off. For some reason, bizarre reason, it ended up thinking that the second paragraph was cryptology. And that could just be because of the training sample that we ended up feeding here. That's pretty unusual. I don't actually quite know what's going on here, but basically mislabeled the second one, labeled the first one correctly. It kind of ballpark understood where the second one should be. And so that's what we kind of see here. You can see it is under science, but obviously it's not under cryptology. We were hoping that it can actually tell us it's under computer graphics. Okay. So I'm giving more of a one-on-one kind of like, not one-on-one, but more of almost like a small group tutoring kind of approach. You'll see this more in like an afternoon lecture style versus a morning style. The morning style, there'll be a lot of exercises that you guys will have to do as well throughout the lecture itself. And Alex can go more in detail about that as one of the instructors. Okay. So now let's take a look at, well, we saw how it did on two different paragraphs. Suppose we want to actually take a look at how it does now on our test sample. So the other documents we did that it didn't get fed in. So prior here, if we actually look above, you can actually see that the training sample was about 11,000 documents. So 11,000 different emails from news groups, were fed. So now we're going to have a totally new 1,500 different articles, and we're going to try to see how our model does in categorizing them. Okay, so that's what we're going to do instead. So we're going to do the same thing that we did prior. Most of this is the same steps as above. Just kind of speeding up through this because of the fact that I want to try to, I know I'm running a little short on time. So we're basically feeding going through all the same steps. We're pre-processing the data and so forth. And now we're going to take a look at just as a classification report, how our model did across the board. And you can see that in terms of count vectorizer, the precision, in other words, its true positives were pretty decent, 80%. True negatives, though, not so hot, roughly about 0.57. Okay, and then our harmonic score between the two is as follows here. And you can also see the breakdown of how many of these each individual articles are actually in the data within the data itself. And you can actually see that the data itself was actually fairly well distributed. And you can look at this classification report as well to see how it did on different topics as well here, for example. So, for example, something like, okay, religion, seemed pretty okay, but that's also because it was very aggressive in guessing religion in this specific instance, because you can see from the recall it was 0.04. Okay, but if we were to look at TF-IDF and see how it did, you'll notice that actually the recall and the precision did a lot better, and that's mainly because of the fact that TF-IDF is a little bit more robust in terms of what it was doing with the text. It essentially penalized a lot of the terms that was ubiquitous across various different articles. So because of that, it was able to be a little bit more robust in terms of its prediction itself. Okay, so that was a lot, and don't worry if like you kind of got a little lost in some parts of it. This topic is actually, I tried to trim. I took basically a lesson that was taught about midway in the course, and I try to trim a good amount of it to make it a little bit more digestible and keep it a little bit high level here.